We began this series of conversations by talking about a view of the history of science put forward by Thomas Kuhn, according to which normal scientists work within what he termed a paradigm. The paradigm determines how scientists do their work, what questions can be asked, what means can be used to answer them, and what constitutes an acceptable answer. The paradigm also sets out a picture of reality. What is the furniture of the universe? What really exists and what are its properties? When normal scientists work normally, they ask acceptable questions, use acceptable methods, and, normally, receive acceptable answers. But occasionally, Kuhn contends, what pops up are anomalies, answers that violate the dictates of the paradigm. When this happens often enough, or conspicuously enough, science enters a period of crisis, where scientists do the things they hate most, become philosophical. That is, start thinking about the paradigm itself. These are the conditions that lead to scientific revolutions and new paradigms. In this discussion, we'll look at cosmology at the turn of the 21st century and see if what is happening there can be thought of as a state of crisis. There are interesting developments around inflationary models of the Big Bang and the positing of, as of yet, undiscovered dark matter and dark energy. Because of problems with our best current theories, new elements are being added to reality, elements we have not yet experimentally or observationally discovered. Is this a simple tweak or the harbinger of something more important in the history of science? Big Bang cosmology came out of both theory and observation. After Einstein developed his theory of general relativity, he applied it to large-scale questions by looking at what it meant for the universe as a whole. Recall that he was deeply disturbed by the result that said that the universe was inherently unstable, always expanding or contracting. He thought that this had to be wrong, and added a cosmological constant to his field equations. The job of this cosmological constant was nothing but to hold the universe still. But Edwin Hubble, in discovering the existence of galaxies beyond the Milky Way, noticed the variability of the redshift of these galaxies. That is, he saw that the farther away a galaxy is from us, the faster it appears to be moving away from us. Further, virtually all the galaxies we can find are moving away. Almost none are blue shifted or moving towards us. Geometrically, this means that the universe is expanding. If it's getting bigger now, it must have been smaller in the past. And so, we posited an event which would begin this process. This event was given the derisive name, the Big Bang, by an opponent of the theory, a name so cute it stuck. When Penzias and Wilson accidentally discovered the background radiation that the theory predicts, it was on its way to becoming a standard part of the paradigm. Received wisdom about how the history of the universe began. But, while the theory has become nearly universally embraced, that doesn't mean it doesn't have some inconsistencies. Problems came to be recognized by the 1970s, problems that would need to be answered lest they become serious anomalies. The first one comes from astrophysicists taking on roommates. Now, the path of the sciences across the board has been hyperspecialization. Each area has become so technical, detailed, and difficult that to work in one as a cutting-edge researcher, it and it alone must become one's complete focus from graduate school on. As a result, the sciences have become largely balkanized with small, often insular groups who hold their own conferences and meetings, who have their own journals, who only talk amongst themselves. Now, this has both positive and negative consequences. But in the case of Big Bang theory, the boundaries broke down. See, if the universe in the past was smaller, then the energy density in it would have been greater. Right? Think back to the metaphor we used about the bubble you blow when chewing gum. Right? As the bubble gets bigger, the walls of the bubble get thinner. Similarly, as the universe expands, the energy per unit volume decreases. But that means that in the past, the energy density was higher. The farther you go back in time, the higher the density of energy. If you go back far enough, the universe would be so hot that things would work quite differently than they do now. The behavior of energy and matter in such hot environments is exactly what particle physicists have been working on. So, questions about the early universe raised by cosmology suddenly became of great interest to and required the expertise of particle physicists. Now, traditionally, astrophysics and particle physics were completely separate subfields. One looked at things that were huge, the other looked at things that were tiny. They had nothing to do with each other. But once we started asking about the early universe, suddenly there was a deep and important overlap that brought these different specializations together. The result was that problems started to arise. Questions about the state of the early universe that came out of particle physics couldn't be answered by the Big Bang theory used by the astrophysicists. And the questions that the astrophysicists were asking seemed to require aspects of particle physics that their colleagues did not possess. As a result, we had three big problems. The first of these problems concerns a class of missing particles, what we call magnetic monopoles. Okay, think back to elementary school when you first started learning about magnets in science class, right? One of the interesting features of magnetism is that, like electricity, there are two charges, right? In electricity, we call them positive and negative. For magnets, we refer to them as north and south. Also, like electricity, like charges repel and opposite charges attract, right? Positive and positive electrical charges push each other away, while positive and negative ones pull together. The same holds true for magnets. North and north repel, north and south attract. Indeed, the equations governing these attractions and repulsion have exactly the same form. We knew from James Clerk Maxwell in the 19th century that electricity and magnetism were related forces. We knew before that we could use one to generate the other, so the symmetry between them perfectly expected. But there's one big difference. We can have particles that have a particular electrical charge, right? We can have, say, electrons that are negatively charged in and of themselves, but we never see this with magnets. Right? Remember that for all the magnets, right? Take, for example, a bar magnet, right? We see that the bar magnet has a north end and a south end. And if you break the bar in half, you don't end up with the north in one hand and the south in the other. No, you end up with two magnets, each with a north and a south. All of the magnets we make are dipolar. They have both a north and a south. We've never seen a magnetic monopole, that is, just a north in itself or a south in itself. The problem is that if our best theory about matter, the standard model, right, which we discussed earlier, if that's correct, then there's a stage in the early universe when the energy density would have been just right to create these magnetic monopoles. Lots of them. Yet, we've never seen even one. Ever. The problem got worse when particle physicists told their astrophysicist colleagues what they would have been like. Hugely massive compared to other particles. So big that they would have hampered the process of creating the sorts of particles we have around us now. The kind that make up the stars and planets and people. The formation of these magnetic monopoles should follow from the Big Bang, and as a result, they should have wreaked havoc on the formation of stable matter. Magnetic monopoles should be plentiful today, instead of the matter we see. But they are at best rare, possibly completely non-existent, while the stuff that makes us up seems to be everywhere. The second problem has to do with an assertion that astrophysicists inherited from Albert Einstein, the so-called cosmological principle, which has been taken as gospel ever since. It is, the universe is homogeneous and isotropic. That means that every place is as good as every other place. There are no privileged points in the universe, and from every vantage point, the universe looks pretty much the same in large-scale structure in every direction. Deviations will occur locally in small neighborhoods, but in the large, the universe looks the same in any direction. Right? Think about the Earth. If you're in the Bonneville Salt Flats in Utah, the Earth seems very different than it would in the Rocky Mountains. Locally, there are differences concerning the topography of the planet. But when we think of the famous pictures of the Earth taken from the Apollo missions, right, we see our planet as a sphere. And any point on the sphere is as good as any other. And the large-scale curvature is the same no matter which direction you set off in. This would not be true if the planet were, say, the shape of a crescent. On a crescent-shaped planet, there would be certain points that were unique, and the curvature would be variable, but not so in a sphere. From the larger perspective, and not so with regard to space in the larger perspective. The problem is that with space, this shape is determined by the density of mass and energy. Remember, that's what Einstein said in the general theory of relativity, right? That gravitation is the curvature of spacetime by mass and energy. Constant curvature over all of spacetime means there's an equilibrium. That some sectors are not more energetic than others, but why should this be? Such equilibrium makes sense if you have small regions, right? If you freshen up a cup of tea by pouring in some newly heated water, right? The tea in the cup will not be uniformly warm at first, right? There'll be hot spots and cold spots, but over time, hot will flow to the cold and the cup will be uniform in temperature. That is, it will have reached equilibrium in terms of its energy density. But there are parts of the universe that are so far away from each other that there could not have been a process that brought them into equilibrium. According to the theory of relativity, the speed of light is the fastest possible speed, and the regions of space are so greatly separated that no process could cover those distances and establish equilibrium. What then accounts for the uniformity? Nothing could cause it without violating the theory of relativity, and yet it's too eerie to be random. The third concern is similar. When we look at the universe, we see that it's geometrically flat, that the geometry of Euclid holds for the large-scale structure. But flat is a special unique point, halfway between positive curvature like a sphere and negative curvature like a saddle. If we were to pick a geometry randomly, the odds of it coming up and it holding across all of space-time as flat, next to impossible. So why is it flat? Why is the energy density equally distributed? And why is it remaining flat over time? If it deviated even a little from flat, that curvature would become exaggerated over time as the universe expanded and the energy density decreased. What accounts for the flatness we see here and everywhere else we look? These were problems weighing down the Big Bang Theory when the American Alan Guth and the Russian Andrei Lind came up with the notion of inflation. If, early in the history of the universe, 10 to the minus 35ths of a second after the Big Bang, for a time of only 10 to the 30ths of a second, the universe underwent a rapid expansion, blowing itself up to a size increase of 10 to the 50th, then we could account for all three of these problems. Okay, first, if the early universe at that time created any magnetic monopoles, the expansion would remove them so far from each other that their density throughout the universe would be nearly zero. It'd be like dropping a single penny randomly in each ocean and wonder why none of them are ever seen by sailors. Right? Further, the expansion would cause a rapid cooling of the universe that would keep the environment that was right for creating magnetic monopoles from being the norm across the universe. The universe would have created many fewer than first thought and scattered them so much that they might never be found. Secondly, it gives an easy explanation for the cosmological principle. Right? Remember that the problem is that we have portions of the universe that couldn't have caused any changes in others, right, that are all homogeneous and isotropic. If the universe had been tightly packed immediately before the inflation, then the parts would have been close enough to be causally connected. The worry about needing processes faster than light would disappear since these parts were in such close proximity. But following the rapid inflation, these parts that had brought themselves into equilibrium would be so far isolated that further influence would become impossible. Third, we had the flatness problem. Right? Of all the geometries, why should the universe be universally flat? The inflation would have to be driven by an energy field. Working out the mathematical form of it, the effect of inflation would be to flatten out space because of the universal expansion, thereby giving a uniform energy density. So, if there was a universal inflation of the sort Guth and Lind postulate, then these three troubling issues disappear. Now, this is not to say that this conclusively means that there must have been a short burst of rapid inflation. We have what the American philosopher Charles Sanders Peirce calls an abductive inference here. That is, an argument to the form, strange phenomenon P occurred. If hypothesis H were true, P would be expected. Therefore, I have reason to seriously consider H. Inflation is not the only possible explanation, but right now it's our best explanation, and most cosmologists accept it. But, as is always the case in science, answers lead to more questions. First of all, what caused the inflation? Scientists don't like unique explanations, and with the possible exception of Germany after World War I, we've never seen an inflationary event like this. What sort of field could it be that gives rise to such a violent explosion of space and time? Now, to be fair, the Big Bang itself is a unique event, and the environment in the immediate aftermath of it would be so uniquely hot that it's not inconceivable that strangeness would result. But in our current best theories, what could possibly explain it? One possibility that's been floated is the Higgs field, the field that gives rise to the Higgs boson. Given that this was only experimentally verified very recently, it seems a possibility. But right now, physicists just don't know. Another problem is the smaller scale irregularities. What caused galaxies and clusters of galaxies? Because of the sort of equilibrium we appeal to in order to justify the cosmological principle, the universe before and thus immediately after the inflationary event would be like smooth peanut butter. Yet a while after the inflation, suddenly the universe begins to look like the chunky variety. Where did the astronomical peanuts, the galaxies and clusters, come from? Inflationary theory has an answer for this. The condensed, tightly packed pre-inflationary universe would be insufficient proximity to give rise to the equilibrium necessary for the homogeneity and the isotropy we see now. But equilibrium is never perfect. Your cup of tea that's been sitting on the table is roughly the same temperature throughout, but there are always small deviations from place to place. The inflation would have distributed these irregularities throughout space in a random way that looks quite like what we see. And the process would have magnified the irregular nature of them such that they would form the seeds necessary for galaxies to form. If the universe had inflated, as Guth and Lin say, then the universe we ended up with should look a lot like ours. But hold on, skeptics say. These seeds planted by irregularities would have been magnified at a time when the universe was still too hot. Protons and electrons may have been able to form in that environment, but the energy density would have made them move around so fast they would have been not sufficiently gravitationally attracted to the irregularities. And that's what's needed to happen in order to form galaxies. Maybe inflation could plant the seeds of the galaxies, but it was still too hot for them to grow. The response from the inflationary advocates is that, okay, yes, this is correct. It was too hot for galaxies to form because normal matter would have been overheated and not subject to the requisite gravitational force. But maybe at this time, it was a different sort of matter that initially found its way to start the process rolling. A kind of matter not made up of the stuff our matter is, a new form of matter which we don't see because it's invisible. Dark matter. Yes, I agree. This sounds sketchy. It sounds a lot like when a child tries to blame mom's broken vase on the action of his imaginary friend. But there were other reasons to suppose that this mystical-sounding dark matter was really out there. A question that astronomers had wrestled with for a while was the mass of things. How heavy are galaxies? How much mass is there in the universe? Now, there are two different ways to answer these sorts of questions. Right? If I walked into my classroom and wanted to know how heavy my class was, I could approach the issue in two ways. I could find out what each of my students weigh, and then add up the weights. Or I could take the class as a whole and put it on some large scale. For galaxies, astronomers did both. They counted the stars in a galaxy, figured out the masses of the various sorts of stars, and then summed up the total. They also figured out the gravitational effects that would give them the mass of the galaxy as a whole. Right? Remember that Einstein's general theory of relativity says that mass warps space so that light travels along the shortest path, so the degree of warping of light around a galaxy will indicate its mass. The problem arose that these two methods, which should have led to the same answer, didn't. The galaxy as a whole was much, much more massive than the sum of the masses of the stars. The gravitational effects of the galaxy meant that there had to be hidden mass, mass we couldn't see. Since the only things we can see are those that glow, those that give off light we can observe through our telescopes, this other mass had to not glow. It had to be dark. In 1975, the American astronomer Vera Rubin found the same thing by examining the way galaxies rotated. In order for them to do what we see them doing, the mass of the galaxy had to be 6 times more than the masses of the visible stars in it. The overwhelming amount of mass in the universe was unobservable by us. But what is it? We can see it gravitationally, but in no other way. What kind of stuff is it? It's dark, so there's no electromagnetic aspect to it, but it has mass. Neutrinos are like that, but they're so tiny they couldn't be it. Because of the similarity, some started referring to the bits of this dark matter as neutralinos. But that never caught on, perhaps because it sounds too much like an Italian weight loss product. Always on the lookout for a great acronym, physicists started calling them weakly interacting massive particles, or WIMPs. They must be massive since they have gravitational effects. The weakly aspect refers to the lack of other interactions, though not necessarily to the weak nuclear force. Theoretically, we would need such particles to make sense in terms of our best theory of matter, the Standard Model. Physicists played with quarks and leptons and tried to see if they could come up with a recipe for the sort of thing we need, but it isn't in there. But it was realized that if we extend the Standard Model with what we call supersymmetry, then we could explain such particles. So, our best theory at present does not give them to us, but it can be tweaked. So, do we see them in the world? Astrophysicists haven't found any. They take it as a point of pride that they are so manly that all the top researchers have gotten together and no one there could find a single WIMP. They're still looking and hoping to figure out how they can detect them. But the theory worked so well that by the 1990s, it was the scientific consensus. The universe was very densely packed, it underwent rapid inflation, and this has been expanding ever since. The only one of the 4 physical forces that works over long distance is gravitation, and gravity is an attractive force. As such, all the matter in the universe must be pulling on all the other matter in the universe, that is, warping space-time in such a way that opposes expansion. Gravity is an attractive force, and the only force that acts over significant distances. As such, it is seen that there were only 2 possible options for the large-scale history of the universe. One is if there's enough matter in the universe, this gravitational pull will be strong enough to stop the expansion and cause the universe to begin contracting. Possibly it could contract sufficiently to create energy density so large that they would give rise to another Big Bang, and perhaps in this way we have an oscillating universe. The other is that there may not be enough energy to fully stop the outward momentum, and that while the expansion will slow, it won't slow enough to stop. Instead, expanding and expanding until the energy density becomes so low that it will extinguish itself, becoming a completely cold, dead universe. It seems to depend on the amount of mass and energy there is, so determining which of the 2 possibilities is the case became a question for astrophysicists. And then there was an anomaly, an answer that was not supposed to be. There were thought to be only two options, right? The universe is slowing and will contract, or the universe is slowing but not enough to contract. In 1998, the Americans, Saul Perlmutter, Brian Schmidt, and Adam Rice, found that the expansion of the universe is not slowing down. On the contrary, it's speeding up. The universe is expanding at an increasing rate. But this can't be right. The only force out there capable of acting over interstellar distances is gravitation. And gravity is attractive. It can only work as a brake. And yet, it's been corroborated many times since, something is stepping on the gas. If gravity is a drag on the universe, and yet the universe is expanding, there must be something else, some kind of energy driving the expansion. What is it? We don't know. But if the invisible stuff increasing the mass of the galaxies is dark matter, then the invisible energy driving the increasing rate of universal expansion would be dark energy. Where is this dark energy coming from, and what is it like? Given the rate of acceleration in the universe, we know how much of it there must be. The answer is a lot. A whole lot. Take the amount of normal matter and energy in the universe, the stuff we originally thought was all there was, this makes up only 1/20th of the contents of reality. Just 5%. Dark matter, that's 1/4, 25% of the furniture of the universe. But dark energy, that's 70% of what exists. The overwhelming majority of what there is in the universe is an energy we can't find. We know where it isn't. Unlike dark matter, it's not tucked away in galaxies and around other clusters of mass. If it were, then there'd be specific gravitational effects other than the accelerating expansion, and we don't see that. It has to be evenly distributed through space. But this is not satisfactory in itself, right? If it were evenly distributed like any other energy field, the expansion would dilute it, like the gum in the bubble. Its density should decrease, and we should be able to detect a decrease in the increase. But we don't. It seems that its density remains constant, despite the universal expansion. It's not like our other energies. Finally, it's hard to find. It doesn't interact with normal matter much at all. So, what is it that's filling our universe and causing it to act so strangely? Don't know. And that's what we mean by an anomaly. We have a paradigm, a picture of reality that includes matter, governed by the Standard Model and Einstein's general theory of relativity. We have the contents of the universe in matter, and dark energy. We don't know what the dark matter or dark energy are. But there's another problem. Our best theories, the ones that give us our methods of figuring things out, the Standard Model and the general theory of relativity, it turns out that both of them have been flawless in their predictions, in their ability to explain virtually every phenomenon that's ever been thrown their way, in their ability to generate novel and surprising predictions. They've been experimentally validated. Trouble is, they can't both be true. The foundations of these theories are inconsistent. If we are to have a successful account of the working of the universe, we need some way to reformulate these theories to make them consistent. What we need is a theory of everything.